Alright, so let's do the second part here. So in chemistry, we're dealing with only three types of particle. They're actually proton, neutron, and electrons. Proton sounds like plus, and it carries one positive charge. Each proton carries one positive charge. And then mole of proton, if you gather up a mole of protons, it weighs 1 gram. Remember that a mole is 6.022 times 10 to the 23. It's a huge number of protons. You just gather it around right here. That's what weighs 1 gram. The neutron, like neutral, so it sounds like neutral. It does not carry any charge, but it has the same weight. The mole of neutrons weighs 1 gram. And electron carries, each electron carries one negative charge. So each electron is counted as -1 charge. A mole of electrons weighs 0 gram. It's actually at 1 divided by 2,000 grams, but it's close enough, it's 0 gram. And for that reason, that electron is pretty much just a super small mass, so we don't really care too much about the electron's mass. All atoms and ions are made of this proton, neutron, and electrons. And if the whole thing is neutral, then they are called atoms. And the whole thing actually has a positive charge or negative charge, it's called ions. So let's just take a look at the periodic table. So I am going to actually get this radon, Rn here. And that Rn actually have 3 different type, or maybe 4 different types, 4 different type of it's called isotope. And some of them actually have, my eyes are so bad, it's 210. So the mass is 210 radon, and then 0 charge right here, right? So it's neutral, it's atom, right? Now, what makes it interesting is that the number of proton in the previous case, right? Number of proton determines the type of atoms. So each of these radon right here actually have 86 protons. So if I actually have 86, right, because you already specified Rn, that means that you already have 86 protons, right? But total mass is 210. We don't care about the mass of electrons. Then rest of the stuff is actually neutron, right? So 210 minus 86, which is 124, right? 124 is neutron. So 210 radon actually have 86 protons and 124 neutrons. Let's do these things with a little bit more interesting ones. The 222 radon. So let me just try to erase the rest of the stuff. So once again, that we are dealing with radon. So according to the periodic table, we should actually have 86 protons, right? And mass of the electron, we don't care. Then how many neutrons do we actually have? It's 1, 136. So it's 222 minus 86, which is equal to 136 neutrons. I may be wrong with the calculations, so you should go check it out, but it's the 136 neutrons. Now you may be wondering, what's this 222.02? where does these things come from? First of all, any of these atomic weight, these are actually atomic weight, but what is it? It's atomic weight doesn't necessarily has to be an integer, the whole number, but what's written here is actually the average weight. So take an example of the xenon right here. It says its average weight is 131.29, right? It's 131.29. So let's just put up this portion right here. So 4% weighs 130, 4% of the xenon weighs 130, and 21% weighs 131, and then 27% weighs 132, right? So if I actually use Excel, if you don't mind, let's just calculate this. So 130 multiplied by 0.04, that's the 4%, right? Plus 131 times that's 0.21, that's 21%, right? Plus 132 times 27%. Oops, not 0.27, right? That's 27%. If I add all of these things up, oops, what did I do? There must be some other things too, right? I think I'm missing something else here. The most important one. There is a 130. Yeah, there are so many other things that's missing here in the table right here. So it doesn't really represent the entire things, but this is really bad exercise. So I'm going to just take these things out. So let's just do the kappa here. Kappa right here is 63.55. I'm looking at the kappa right here. It said 63.55. So something that I know from the when I was a student. I remember this kappa stuff. So kappa, average mass, is 63.55. Now, kappa has the isotope. Some of the kappa weighs 63 grams, and then some of the kappas weighs 65 grams. I believe that the split was 70-30%. So this one is 70%, and then that one is like 30%. Then the average mass is going to be 63 times 0.7 plus 65 times 0.3. It's approximate. Oops. 0.3, right? Okay. So if I do this, then it's close enough. It's but I have this number is close enough. So it's this one right here is literally the average. like the average mass of the kappa is actually written in here. I'm going to talk about this average mass a little bit more, because that when we actually start solving the problems, then you're going to have to deal with your own calculations. So yeah, we're going to deal with that one later. So find the number of electrons in xenon. So let's just go back to the previous problems. So xenon is having this particular block of information I have. Now what can I say about the xenon right here? Xenon right here. Now, not much of the information, right? I don't know anything about each isotope mass, but something that clear from this sentence right here. I know that mass of the xenon, not mass, that the number of proton is 54, right? That comes from this guy right here, right? So number of proton is 54. Proton is 54, right? And there are some other things that's sort of like hidden here. What's the charge? The charge is 0, right? Then remember that I have 54 protons. Each of those carries positive 1 charge, right? So now I have a 54 plus, but entire things has to be neutral, so I have to have 54 negative, right? Then how many electrons do I have? Actually 54, right? Because each electron carries negative 1 charge, right? So I have to have 54 electrons. What is the number of protons in xenon? It's 54 protons, right? What is the number of neutrons in carbon? So let's just take a look at this carbon right here. I don't know if you can actually see this one, but it's 12.00 something. So it's close to 12. Then carbon is 6. Carbon is 6, and then that mass is 12. Something like this. In a periodic table. Well, no, something like that, right? And then if I write these things in the normal format, it's something like this. As soon as I wrote the letter C right here, then I have 6 protons, right? That comes from that number right here, right? And then how many neutrons do I have? We don't care about the number of electrons, because they don't weigh a thing, right? So 12 minus 6, the total mass minus the mass of the proton is going to give us the mass of the neutrons, which is 6. So 6 neutron right here. So that's probably completes the atoms. Now we're going into the molecule. The molecule is a collection of atoms. So if you actually start out with 3 different atoms like H and oxygen, right? And then release it to the just release it in the closed container, and then eventually you're gonna end up with the group of atoms get together to form this H2O. It looks like this. And those are called molecule. And the molecule, the only requirement of molecule is it has to be stable. Right? If it's not stable, then it is not going to last very long. So it's the molecule has to be a stable structures. So if you release all these atoms and then somehow that magic of the chemistry that it changes the locations, and then that it forms a molecule, and that molecule happen to be very stable, then you can actually call it as a molecule. Really, so that's the molecule. So by grouping so many different atoms into one molecule, you can actually create a whole bunch of stuff. In fact, everything that you can see around you is a type of molecule. So the simple one is ethanol. Ethanol look like water, but it does actually have C2H5 on one side and then OH on the other side. So yeah, the millions of molecules that you can come up with, and then that you're gonna deal with the molecule from this point on in this class. So each of these molecules, this may not be that accurate, but about 90% of the time that you are going to find exactly the same structures. So H2O, I wrote it as sort of like a bend shape molecule, look like this, right? You're not gonna find the H molecule with a straight line. It may actually rotate in orientations, but they are same, right? These are same. These are same, right? But this is not. Relative position is important, right? So if you actually have the shape like this, no matter how you rotate, it's the same shape. Right? You're just changing the orientations, right? So they're same, these guys are same, but that one right here is different. And what I'm telling you right now is that these things right here doesn't happen. It's pretty much the structure is often it's unique. All right, so every ethanol looks like this. It's always. It may rotate, but it may rotate like this, but the shape stays the same. Relative position stays the same. So for that reason, that instead of writing the picture like this, we are going to write everything in terms of the symbol right here. So this structure right here have 2 hydrogen and 1 oxygen, right? So we're gonna write it as a 2 hydrogen, 2 goes to the subscript right here, and then 1 oxygen, 1 is hidden here. This one right here, I have 2 carbons, right? And then 6 hydrogen and 1 oxygen. So write it like this. Now, if I actually have 2 water molecules, so like something like this, right? I have 2 water molecules, right? Then you actually write 2H2O. That 2 is multiplying everything by 2. So hydrogen, I have 4 hydrogen here, right? Because 2 multiplied by 2, I have 4 hydrogens. 1, 2, 3, 4. 2 multiplied by 1 oxygen, so it's 2 oxygens. So I have 2 oxygens right here. So be careful about the position of the numbers right here. That 2 right here means that each molecule have 2 hydrogens. Okay? For example, like this one, each ethanol molecule contains 6 hydrogens, 2 carbons, and I may actually have 5 C2H6O. In that case, how many carbon atoms do I have? It's total of 10, right? Alright. Should probably stop here.